So, good evening to everyone and welcome to our 50th research seminar in probability and statistics. Today we have with us Ismael Lemhadri, and I would like to thank Ismael for having kindly accepted our invitation to present this seminar. I also would like to say a few words about Ismael. Ismael completed the undergrad studies in France at École Polytechnique in applied mathematics. He holds a master's degree in statistics from Stanford University, and in the present he is a PhD student in statistics supervised by Professor Robert Tibshirani at Stanford University with a minor in computer science machine learning track. He has been involved in teaching and research in areas related with data science and statistics. And today, Ismael is going to present a talk entitled LASNet, a Neural Network with Future Sparsity. And this is a joint work with Frank Ruan and Rob Tishiriani. Okay.
Thank you very much, Isabel, for the introduction. I'm very happy to be here. Right now, it's actually the morning here in California, 8 a.m., just starting the day. I know you are actually finishing your day, so I will try to keep your attention. Thank you for attending. And I will talk about a topic that I've been working on in the recent past with my advisor and Fong, who is a former student of the statistics department here at Stanford, who is now doing his postdoc at the University of Berkeley with Michael Jordan. And the talk will be broadly in the area of machine learning. I'm going to tell you a little bit more details very soon, but just to give a brief introduction about what I mean by modern machine learning. In a lot of applications, recent applications and problems these days, what we observe is that there's larger and larger models being used in real life applications, and these models tend to be applied to massive amounts of data. And this is, I'm showing here just an example of a visual example, a pretty artistic example, if I may say, of a neural network architecture that is specifically used for computer vision. And there's been, as you all know, tremendous amounts of progress in computer vision tasks recently. And one of the highlights of this progress has been shown in this computer vision competition, where over the last 10 years, the performance of the best model, of the winner, has dramatically decreased. Where 10 years ago, the best model had accuracy about 75%, so error slightly more than 25%, and those models tended to rely on very, very different techniques from what's happening right now, but they relied on ideas from hidden Markov models and mixtures of Gaussians and support vector machines and very heavy feature engineering. But over the last few years, essentially starting from 2012, if you might notice on this graph that the best winning model always ends with a net, and that is to say that it's a neural network. Every year the winner has been a different one. So just to say that speaks volumes about the amount of research and human efforts that have been going into these competitions. And right now we have seen pretty dramatic improvements. I don't know if we'll ever reach the 0 bar, but we might not be too far from that. And deep learning obviously is a huge area that has provided the winners to all these recent competitions, but has actually applications in all sorts of fields and areas. It's not an exaggeration to say that deep learning is a big revolution to the world of computational science, and to a lot of predictive tasks. One example is in healthcare, where a lot of work has been going into assisting the diagnosis provided by doctors in a way that can sometimes actually improve on the classification accuracy on and the quality of the diagnostic provided by doctors. There's a lot of efforts in drug discovery as well. They're fairly heavy on the computational and simulation side, where the goal is to do a lot of, there's a lot of brute force engineering and simulation going into trying all sorts of molecular combinations and designs and testing them in terms of their chemical processes in order to find some potentially relevant drugs for treatment. And of course, recommender systems are another application, but there's many others. Gene sequencing, advertisement, speech recognition problems. Essentially, the moment you have a problem that has a very rich data setting where the number of observations is sufficiently large, then you might consider throwing a sort of black box algorithm like this if you have enough computational power to just train your model on it, and you might get the best performance using a deep learning based model. But of course, sometimes the desiderata or the mandate of the method goes way beyond just prediction accuracy. And for example, I mentioned healthcare as the first example. And in an important application like healthcare, it's not enough to just make a good prediction on test data, but if you were to actually go and use this method in real life, then the physician would probably want some sort of guarantees about the method that they are using. And a guarantee here might not take the form of a theorem, but it would be closer to an interpretability guarantee, where the model not just outputs a prediction, but also explains how they came about that prediction. And that is a very important way of just increasing the credibility and the trust that the domain expert puts in that method. So I would like to approach that problem today from the perspective of feature selection. Feature selection has a lot of other benefits besides just interpretability, and I've listed a few of them here, and I'm sure everyone generally likes to think about it from a different perspective. But essentially what happens is in many problems of interest, a lot of the information in the features is just irrelevant for predicting the responses, and only a small subset is informative. And feature selection methods provide insights into the relationship between features and a certain outcome. And they do that while simultaneously reducing the computational load of the learning task by removing features that are redundant or noisy. And I've shown you examples of high dimensional data sets. These are becoming ever more prevalent, and therefore feature selection has seen widespread usage recently across all those real world tasks with benefits that include reducing experimental costs, enhancing interpretability, computational speed up while training the model, reducing the memory required to store the model, and even improving model generalization on unseen data. So for example, feature selection is especially valuable in biomedical studies where the data with the full set of features can be expensive or difficult to collect. And these techniques can alleviate the need to measure irrelevant or redundant features and allow you to focus and really identify a small set of features while maintaining prediction performance. And this has been possible because, in practice, because really we observe a very good trade-off between the number of features that you might need to keep and the statistical performance. So as a motivating example here, I'm showing a data set that consists of the expression levels of various proteins across tissue samples. And these measurements are increasingly carried out to assist with disease diagnosis, because biologists will go and measure a large number of proteins with the aim of discriminating between disease classes. And it's still expensive to conduct all of the measurements that are needed to fully characterize these proteomic diseases. So it's a natural question to ask whether there are any redundant or unnecessary features, what are the most effective and representative features to characterize the disease. And in addition to that, when a small number of proteins are selected, their biological relationship with the target diseases is more easily identified. So these marker proteins will provide additional scientific understanding of the problem. And in this figure, I'm showing an example of a feature selection path that was produced by our method on this mice protein dataset, which contains expression levels of normal and trisomic mice that were exposed to different experimental conditions. And this sort of curve that you see here is actually very typical, this steeply concave curve that tells you essentially that with just that the method basically captures 70% of the signal with about 20% of the features. So the trade-off between the number of variables kept and statistical performance is pretty good, and that is very desirable when you consider the cost of proteomic measurements. And so, and then you're able to narrow down the list of important variables, and that also makes the conclusions of the prediction tasks more actionable. In terms of broad areas where feature selection methods can be divided, there's generally three groups. The first two are filter and wrapper methods, and then I talk about embedded methods briefly. And filter methods operate independently of the choice of the predictor by selecting individual features that maximize some desired criteria. For example, there's the popular Fisher score that selects features such that in the data space spanned by the selected features, distances between points in different classes are as large as possible, while distances between points in the same class are as small as possible. And filter methods tend to select features independently of the learning method that will be used. And this is a major limitation. For example, filter methods, they only evaluate individual features, so they're generally not able to detect features that mostly participate through interactions with other features. And on the other hand, wrapper methods use learning algorithms to evaluate subsets of features based on their predictive powers. So there's been a lot of recently proposed methods, some of them based on mutual information criteria like the HSIC lasso, and others that use kernel-based techniques to discover nonlinear feature interactions. And similarly to wrapper methods, embedded methods will use specific predictors to select features, and they're generally able to detect interactions and redundancies among features. But in addition to that, embedded methods will tend to do so more efficiently because they combine feature selection and learning into a single problem. And a well-known example of an embedded method is the lasso proposed by Rob Tibshirani a few decades ago, and a very popular and effective tool in many problems. So these methods can be used to select features for regression or classification by varying the strength of this L1 regularization. However, one of the limitations of the lasso is that it only offers solutions to linear models. And the desiderata from which I would like to tackle the problem today is really that we'd like to go beyond this setting and to propose a general method that can capture both linear and nonlinear relationships between features and the response. And I would like to do that from a non-parametric perspective that doesn't involve optimization inside a restricted class of functions. So the proposal today is a new approach that extends lasso regression that will be based on a certain hierarchy principle that I will tell you about, and that is in the context of feed-forward neural networks. The method is called LassoNet. It uses a certain residual connection in order to satisfy the hierarchy principle, so that a feature neuron is active only if the linear connection is active, and the linear and nonlinear components are optimized jointly. But before I tell you the details about the method, I will just show you as an appetizer the results of using LassoNet to select the informative pixels on a subset of the MNIST dataset. This is the standard benchmark dataset for handwritten digit classification. And here I'm showing digit classification task for digit 5 against digit 6. And I'm showing you the classification accuracy by number of selected features. And then these 3 graphs are a sample from the model with 160, 220, and 300 active features. And in this example, LassoNet selects the most informative pixels on a subset of MNIST and classifies the original images with high accuracy. So to tell a little bit more about the method, I will start by describing this hierarchy principle, which is pretty grounded in statistics, actually, more not in machine learning. It started was started by George Cox as a principle, who said that large components' main effects are more likely to lead to appreciable interactions than small components, and that the interactions corresponding to larger main effects may be of more practical importance. So there's been basically the idea is to give prominence to the linear part of your model, but to also include additional terms. For example, there's been recent work on Lasso for hierarchical interactions that include quadratic and pairwise interaction terms, and these are important and relevant to extend the depth of the breadth of the technique and the function class as a whole. But and this was an important first step, but it did not address the general case of arbitrary nonlinearity. So we'd like to the approach we'll propose today. It essentially guarantees a sparse solution that is sufficient for capturing both linear and nonlinear relationships, that doesn't involve optimization in this restricted class of functions, but that obeys this hierarchy principle that will tend to stabilize the model. And the method is shown here as a neural network architecture that uses a residual connection. The residual connection is shown in green, and then there is an arbitrary feed-forward neural network. It's shown in black. So after each gradient step, the residual layer and this first hidden layer is the one that I will focus on, actually, because we'll care about selecting features from the input, not about selecting features inside the network or specifying the inside of the network. So the focus will be on that. And here I state the objective function for the method that basically has a regular loss term that is just dependent on some parameters. You know, theta, what I call theta here, is the linear residual connection that was shown in green, and W, just in an arbitrary, very general notation, is just the weights of the neural network. And the objective function is that of the regular loss that you might define, and then I add an L1 penalty term into the model, and I have a penalty term, L1 penalty, only on the linear components. And the nonlinear components are governed by this additional constraint. And this constraint can be seen as an embedding into our method of David Cox's principle. So specifically, if you look at every constraint here, you will notice that it budgets the total amount of nonlinearity that involves every single input feature according to the relative effective importance of that feature as a main effect. And an immediate consequence is that that feature will weights will all be set to 0 as soon as the linear connection is 0. In other words, the feature is completely inactive from the model without the need for an explicit penalty on the neural network's weights. And this provides efficient feature selection. And I will mention right now that a key property is that the linear and nonlinear components are fitted simultaneously, and this allows to capture arbitrary nonlinearity in the data. For example, if the best fitted model has larger linear weights than nonlinear weights, if it has only moderate nonlinear weights, then this can be accommodated with a reasonable choice of the control parameter n. So the demand for hierarchy is analogous to the demand for sparsity. It's a form of regularization. These are the two hyperparameters. The lambda penalty is familiar to, I'm sure, to all of the audience here. It's the classical L1 penalty that encourages sparser models as you increase the value of lambda. And then there's the hierarchy parameter n. Now, I'll go a little bit into the training of the model. The training involves two steps. I'm showing you this, I'm showing you this, the training loop here. I don't expect you to read over everything here. It's just just a few lines, but I would like to show you an example again, going back to that feature selection path. And these were the results on the mice protein dataset, where we didn't take the number of features to select as a given, but really we looked over the entire path from 0 to all possible features. And here, a key difference actually between the training of Lasso and L1 based models and LassoNet is in the way you go over the path. In Lasso based methods, you will go over the path from sparse to dense. What that means is that you will start from the left and then progressively increase the path. But this is not what we do here. Actually, we actually start from dense to sparse, meaning that we start from the right and then go over the path in a fashion that is like pruning the model. And I will tell you in a few seconds why we are doing that. So I want to put the emphasis that on the way the path is being trained here. The main two novelties is that we're going over the lambda path from dense to sparse. That means that we increase the lambda path over a logarithmic scale, and we tend to regularize more. And then the key algorithm that allows to perform this optimization is a hierarchical proximal operator that I will also tell you more about. So to get back to the to that dense to sparse approach, basically the technique of warm starts is the effective techniques that is used here. It's very effective for optimizing models over an entire regularization path. In Lasso L1 regularized linear regression, it's optimization is carried out for each fixed value of lambda on a logarithmic scale from sparse to dense, and using the solution from the previous lambda as a warm start for the next. And this is effective because the sparse models are easier to optimize, and the sparse solution is usually that of main interest. But it turns out that for optimizing LassoNet, a dense to sparse approach with warm starts is far more effective than a sparse to dense approach. And what that means is that the dense to sparse approach returns models that generalize far better than those returned by the sparse to dense approach. So I'm illustrating this phenomenon in figure 4, where the standard sparse to dense approach gets caught in local minima with poor generalization ability. And on the other hand, the dense to sparse approach leverages the favorable generalization properties of the dense solution and preserves them throughout the path, even after drifting into these sparse local minima. And so training over the entire path combines these warm starts and then early stopping criterion that's very common for neural networks. And I will mention that in terms of the computational complexity of the model, really, training the entire regularization path can be done at an attractive cost, because the bulk of the cost will occur when training the dense model. And training the regularization path is computationally cheap by exploiting warm starts and effectively amounts to pruning. So this distinguishes actually our procedure from most existing feature selection methods, which require advanced knowledge of the optimal number of features to select. And they're not able to leverage the existing solutions when varying the number of features. Now to the optimization section. I mentioned that hierarchical proximal operator. So the objective will be optimized using proximal gradient descent. The novelty is a numerically efficient algorithm for the proximal inner loop that we call higher prox. So essentially, this optimizer is derived from analyzing the optimality conditions that will characterize the global solution of a certain non-convex minimization problem that defines the proximal operator. And it turns out that this inner loop is decomposable or separable across features. So there will be a separate optimization problem to solve for each feature. And the complexity of a higher prox is actually just that of sorting the parameters that need to be updated. So this will generally be very negligible overhead compared to the cost of computing the gradients with respect to the same parameters. And I will also mention that implementing this optimizer is straightforward in most standard deep learning frameworks. And now I will tell you a little bit about the experimental evaluation. But before I do that, maybe I can take a few moments to answer any questions you might have about this. Or if there are no questions, I will just continue. It looks like I can continue. If anyone wants to ask a question, please feel free to just unmute yourself, and I'd be happy to take your question. So now I'm moving to the experimental evaluation, and I will show you experimental results on several real-world data sets. These data sets will be drawn from several domains, but before I tell you about the data sets, I will actually just mention the methodology used here. The methodology is a bit special because, like I said in the beginning, we have different sorts of feature selection methods. Some of them are embedded, some of them are not. The not embedded methods do not provide a prediction or a output. They just select the relevant features. So that's not very helpful when I compare different feature selection methods. From a machine learning perspective, I'm generally interested in predictive accuracy. So I generally want to see the performance of the model using a reduced number of features. But if the feature selection methods don't provide a prediction, then there is no obvious way to do that. So instead, what I will do is I will consider all those other feature selection methods, which are not integrated procedures that simultaneously perform feature selection and learning, but I will explore the use of the selected feature set as input into separate downstream learners. So for each task, I run each algorithm that is being evaluated to extract a number of features that is selected. And I do that for a fixed number of features because most other methods take as input a given number of features. And then I will measure the classification accuracy by passing the resulting subsets of the data with just those selected features into two downstream learners. One of them is a one hidden layer feed-forward neural network. And another one is an extremely randomized tree classifier. And that is actually a variant of random forests that has been used with feature selection methods in the past. And of course, there is a number of hyperparameters to care about. So there will be the learning rate, there will be the choice of the optimizer, the number of hidden layers, and all those were conducted using a standard approach for training networks, which rely on having a validation set to select the optimal number of, the optimal choice of those parameters. And the results are displayed for the best model chosen based on that validation set, and they're displayed on another held out test set. So I divide data sets randomly into training, validation, and test. And I cross-validate the number of neurons, for example, in the hidden layer, and the network with the highest validation accuracy is selected and measured on the test set. And I try to look at data sets from several domains, including protein data, image data, voice data. Those data sets have all been used for benchmarking feature selection methods in prior literature. I mentioned in the first few slides my protein data set. That was the motivating example for the study, because the data is interpretable and meaningful, and it's a potentially important task to select a small number of proteins to and have maybe engineers or biologists analyze them separately. But I will also present results on other data sets where the features might not make as much sense if you look at them individually. For example, on MNIST data, the features are just grayscale images of handwritten digits. But I chose those data sets because they're widely known in the machine learning community. And although they are image data sets, the objects in each image are centered, and that means that we can meaningfully treat each of the pixels in the image as a separate feature. So I won't give more detail about all of the data sets here, but I will show you maybe just a graph to begin with. These are the results on one of the data set, the ISOLED data set, which consists of pre-processed speech data of people that speak in the names of the letters in the English alphabet. That's widely used as a benchmark in the feature selection literature. And each feature here is one of the 617 quantities produced as a result of pre-processing, and those include spectral coefficients and sound features. So the results are shown on the ISOLED data set, and here I compare ISOLED to other feature selection methods using both the hidden layer network and an extremely randomized trees classifier. And we find that across all values of K that are being tested, and for both learners, ISOLED has the highest classification accuracy. And here I'm comparing the results over several other data sets. So the classification errors are shown in this table for, again, both the decoder network and for the tree classifier. But here, actually, I'm only focusing on the decoder network. And overall, we find that the method is the strongest performer in the majority of cases. Occasionally, you may see that more than one method achieves the best accuracy, but in most cases, the method either ties or overtakes the remaining methods in all these instances. And this might suggest that our hierarchical objective may be widely applicable for different learning tasks. So that, for example, the COIL20 dataset is also a grayscale images dataset. Then there's this activity dataset, which consists of sensor data collected from smartphone mounted on subjects while they perform several activities. And I also have a second line here, which is for MNIST fashion, which is very similar to MNIST in terms of the dimensions and the size of the data set, but it's again, grayscale images of clothing items. It's a slightly it's a more difficult task than MNIST. It's considered, I mean, it's a bit more varied. It has more classes. Sorry, it has more different items, and that's generally a useful complement for MNIST.
Can I ask a quick question?
Yes, of course.
Do you have how many features were selected in each case? Do you have an idea of those numbers?
So here I'm taking a fixed number, k equals 50.
Okay, 50, okay.
And again, here I had to choose a number of features to select because the other feature selection methods require a number of features to select in advance. And they don't do this data-driven feature selection over the entire path where you might go and look at the optimal number of features to select yourself. But so I had to make this choice of k equals 50, but it could have been k equals 100 as well, or any other number. But one thing that's not mentioned in, that doesn't appear in this table is that the other methods took k equals 50 as given, and they did all of their training there, but Lisbon has actually provided the entire feature selection path, and it provided that entire path essentially at the cost of training a single model, which is that at k equals 50. And there's no mention here of the computational cost, but it is an important consideration in real life. Any other questions? If not, I will just try to provide a brief summary of what this talk has covered. I started by giving a certain motivation for neural network-based methods and why feature selection is important, and some of the shortcomings of existing feature selection methods. I presented the method from the perspective of really selecting features in a non-linear way and doing that over an entire regularization path. This is perhaps the most important items to keep in mind. This hierarchy principle is pretty natural. You might have seen or heard about it before, but really the key benefits is that the method is data-driven and provides a path of regularized models at a cost that is essentially that of training a single model. And at its core, the method is based on a non-convex optimization problem. So we are doing regular gradient descent on vanilla gradient descent on the neural network. Of course, there is no guarantees about that you'll find the global minimum of a neural network solution. That's just not possible. So we're just using a standard optimization framework, and we're adding really just a few lines of code that are needed to apply this hierarchical proximal step in order to satisfy the sparsity requirements. So if you're using Adam as the optimizer for your neural network, you will just use it again, and then you just go over the path after you finish training the dense model by applying that hierarchical proximal step. And in order to do that, we needed an efficient solver for that non-convex optimization problem. The non-convexity was due to the constraint that is introduced, but it turns out that by analyzing the optimality conditions, we can derive the global solution to that non-convex optimization problem. So the method relies on the stochasticity of the initial dense model in order to efficiently explore, and then the landscape, and then it will converge over the entire regularization path with different numbers of input features. So this makes the method different from many feature selection methods that assume prior knowledge of the number of features to select. And other advantages of the method include its generality and ease of use. It's straightforward to implement the architecture in popular machine learning frameworks by just modifying a few lines of code from a standard feed-forward neural network. and the runtime of the method is competitive. Its runtime over the entire path is similar to that of training a single model. It can improve with hardware acceleration and parallelization techniques that are very common in deep learning. The method only has one additional hyperparameter compared to L1 methods, which is the hierarchy coefficient. And we find, based on our empirical studies, that the default value of m equals 1 that was used works well for a variety of data sets. Now, there is a few, of course, this is not finished work. There's LaSonnet there's a number of extensions that would be interesting to consider. And what I'm showing here is an unsupervised learning case. So unsupervised learning can be important because in certain applications, specific prediction tasks may not be known ahead of time, and therefore it can be important to develop methods that can identify a subset of features while allowing imputation of the remaining features with minimal distortion for arbitrary downstream tasks. So an unsupervised approach is relevant in order to identify the most important features in the data set and whether they're redundant features that do not need to be measured. And it's actually pretty straightforward to adapt LaSonnet to the unsupervised setting by replacing the neural network classifier with a decoder network. So this is essentially just changing the last layer of the network. Rather than outputting a prediction, you will try to actually output reconstruct the input. So you will be looking at a reconstruction loss. And really the pseudocode is quite similar to that of training the standard LaSonnet. I will mention that just the major difference is the use of the group lasso penalty in order to enforce the same set of selected features across all reconstructed inputs. So there is a group version of the hierarchical proximal operator. There's a very related work here that's the concrete autoencoder. There's also a number of extensions and applications to other settings, like the Cox proportional hazards model. This one is widely used model for survival analysis, and in the standard formulation, the model is linear in the covariates, and it turns out that there's been work on improving those survival models by using a more complex, nonlinear modeling of the relationship between the covariates, say, of the patients, like the clinical and the genetic features, and then the survival times. So rather than doing a linear Cox proportional hazards model, we will use a neural network-based method for modeling the survival times. This is actually existing work that did this transition from linear to nonlinear. And right now we're investigating, just because of the generality of the method, we can just take the LaSonnet optimizer and plug it into the existing architecture for that so-called deep serve model. And that would allow simultaneously to perform nonlinear, much more general modeling of the covariates, and at the same time to select the relevant covariates from patients. Again, if those covariates include genetic features, and maybe there's a lot of them, and maybe we just want to focus on a small number of those. And another line of work is, which is actually work in progress, has to do with matrix completion problems. This is a fairly popular framework that was popularized by the Netflix competition, for example, where there's a lot of missing values, and the goal is to impute these missing entries based on the observed entries. So there is existing methods that make a common assumption, that is that the underlying matrix lies in a low dimensional manifold, like the soft impute method assumes that the matrix is low rank, and then it turns out that here there's an iterative algorithm that does this imputation by using essentially principal components. And what we would be doing here is performing a more general kind of imputation that does not make a low rank assumption on the matrix, but that just uses a small subset of features to do that imputation. And again, this is also a different but similar kind of regularization because it's the fundamental assumption behind these matrix completion methods that only there's a low dimensionality somewhere, either in the input features or the rank. And here the extension would be that we can have a low dimensional but possibly nonlinear submanifold. So the method could be similar to self-impute, but exploits the possible nonlinearities in the features. So this is all I had to say for today. I have made the materials for the talk available online. The slides can be downloaded if you'd like to go over them again. I've also made the code publicly available, and I would like to thank my advisor, Rob, for guiding me in this project, and Fong for his help as well. And the project was actually implemented in PyTorch, which is one of the most popular deep learning frameworks. There's essentially either PyTorch or TensorFlow, which shows PyTorch here. So I'd like to thank Louis Abraham for helping me with the PyTorch implementation. And thank you all for attending the talk today. And I'll be here if there's any questions.
Thank you very much, Ismael Lemhadri, for your very, very interesting talk. I would like to ask if someone have any questions or comments for Ismael.
I do have a question. Is that okay?
Please, yes.
Turn on my camera, just a second. Hi, Ismael. Thanks for the talk. Can you hear me?
Yes, absolutely.
Thanks. It's very interesting work. If I fully understood, so the linear part is essentially guiding the feature selection, right? Mm-hmm. And it's essentially L1 regularization on the linear part, although the loss is more complicated. And it is known that L1 regularization or lasso is very fragile in the presence of highly correlated features. So does this inherit this problem?
So that's a good question. The fragility of the lasso in terms of correlated features, my understanding is that if there's a lot of correlated features, lasso will select one of them. It may not be clear which one is being selected, but if they're highly correlated, then perhaps it doesn't matter exactly which one is being selected, so long as they have similar reconstruction or imputation performance. And the truth is that the exact choice and stability of the method strongly depends on the choice of the optimizer that is used for training the dense model. Before going over the entire regularization path, you need to train an initial, say, neural network just using any standard optimizer. And there's been a lot of work on that area of stabilizing and making the prediction set of the network consistent across multiple runs. Like you will start from a random initialization of the network, and then you will train it using gradient descent. You might get a different solution at each time. There is no guarantees on that, but this is an active area of research, and we are using the Adam optimizer, which is perhaps the most effective for tasks like this. It's a second order method that has an adaptive learning rate for each feature. So generally speaking, the stability of the method really relies on the stability of previous, like the first item in the pipeline, which is the choice of the optimizer. And that is like a huge area of research in deep learning based methods. And that is how I see it more than from the L1 perspective, which is more of a pruning perspective that happens at a second stage.
Thank you.
Any
So
more
if anyone else
questions?
has questions, I have another one.
Yeah.
So sorry for the question about the number of features, because I hadn't noticed that you had the k equals 50 at the top of the slide. But your question actually, your answer actually brought the next question, which is, since you have the whole regularization path in your method, is k equal 50 the best result for LassoNet, or could you do better than that?
Oh, that's a great question. Actually, we have, just yesterday I was adding a new column to this table. Sadly, I didn't update the slide with it, but essentially it's the method that the model using all input features rather than just 50. And it turns out that in some data sets, using 50 or say 400 doesn't make much of a difference, because the first 50, the most important 50 are enough to impute most of the signal. But in other cases, that's not the case. We did not do a very careful choice of the number of features to select. We just took k equals 50 because it fits well for all data sets. Some of them only have 70, so we wouldn't been able to choose, say, 100 for this one. But really, we could technically do a different systematic analysis. For LassoNet, it's straightforward because we have the entire path of features. But for the other methods, you have to run every method again for every choice of feature, and that is computationally expensive, especially when you have larger data sets.
Thank you.
But yeah, that's a great question. I wish there was a systematic way of doing this, like generalizing or extending this approach of using the existing features for a given number and leverage that knowledge for another size of the feature sets.
Any more questions or comments?
I have a quick one. I don't want to monopolize the questions, but if no one else. So have you thought of replacing the L1 norm with ElasticNet to handle those situations where they have correlated features?
So essentially, you're suggesting adding an extra penalty in addition to the L1 penalty, which would be an L2 penalty.
Yeah, exactly.
And that would have potential other benefits like regularizing the network and helping with correlated features and so on. That's potentially an interesting thing to do. We didn't do it actually in our experiments because the focus really has been on feature selection more than on regularization. But it's true that the method has a regularization perspective as well, because we're implicitly capping the weights of the neural network, and that can only regularize it. So it could be interesting to perform a systematic in-depth analysis of the regularization properties of LassoNet. And one way to do it could be by adding an L2 penalty, which is standard in deep learning.
Yeah, thanks.
Hi, may I ask a question?
Oh, hi. Yes, of course.
Yes.
Hi, I'm Carlos. I just wanted to ask, I got the impression that you were using this on fully connected layers. And could you extend this to convolutions?
Very interesting question. In all of the experiments I've shown you, the focus has been not on convolutional layers. That's true. We focus on fully connected feed-forward neural networks. And we've taken data sets where the input features were very meaningful and it's made sense to select individual features and to analyze them, like proteins, for example. And as it turns out, there's many other situations where the input features do not make much sense, but really what is done is relying on the neural network to build the relevant features. If it's a computer vision task, then the input features can be very arbitrary and change a lot from image to image if the images are not centered and so on. And in a setting like that, it doesn't make much sense to select the input features. And instead, it would be more relevant perhaps to select the filters that are chosen. If you have, say, an image data set with 1,000 filters there, because it's been trained on all of ImageNet, and now you just want to have a sub-classification task, which is, say, cats against dogs, then you just want to find a subset, a small number of convolutional filters that are relevant for classification of cats against dogs. Maybe you don't need all of the input features. So we didn't actually perform an analysis like that in this paper, where the feature really has been on this like proper feature selection. But you could imagine taking the LassoNet model and adding a residual layer later in the model, after maybe after the convolutional filters side, and then what you would be doing would be to select the relevant filters. From the technical perspective, all the tools you need are already here, because you only need this group lasso actually penalty. The filter won't be a single feature, but the filter might be an entire patch, and then you might want to select like a group of features that constitute a patch, and to do that you might use a group operator like this one. So the technique is there, it just remains to be tried, and it could be an interesting extension to this work.
So anyone wants to make another question, or?
This is, hi.
Hi.
This is Raquel Gaspar from University of Lisbon, from finance. So, given your experience with these methods and neural network, I have done some work with neural networks, but I'm thinking of applying it to credit risk. Do you know any credit risk application of neural networks?
Interesting. I would take the on the choice of the specific domain, area, or application. Well, I would first ask myself, what sort of features am I interested in to select for? Am I actually interested in feature selection for credit risk applications? That's maybe from the domain knowledge perspective, and that's a bit outside of my own knowledge, okay, because I'm not an expert in finance. But another perspective I could bring is that of just the size of the data sets. And in all of the data sets that I'm showing here, the number of training points is significantly larger than the number of input features. And this is really what I call the data-rich problems. This is an important feature or characteristic of these settings, because neural networks are black box algorithms. They don't assume or do any sort of prior modeling of the output. They just rely on large amounts of data to learn the patterns. So if you have a data set where you could call a data-rich problem, then it could potentially be an interesting application.
If you think in terms of a bank giving credit to people, we are talking about millions of people or thousands, depending on which bank you have the data. And in terms of the input variables or the features, then you have personal characteristics of the person, as well as social income, stuff like that, right? Mm-hmm. And then you have a training database, which is the past, where you can check default before. So
so it would be a binary, maybe.
Yeah, 0 or if it's in between. I mean, we can, if possible, use to predict kind of likelihood of default. Then it's not so binary. I
see. So likelihood of default, probability of default, that's all very standard. Like if you take a logistic regression model, the output would be a probability.
We want something different with the big data.
Yeah, exactly. In a neural network, you would have a softmax layer at the last layer that converts the weights into an output that's between 0 and 1. And it would it perfectly makes sense.
Okay, thank you. It was just an idea. Okay, thanks.
Thanks.
So any more questions or comments? So if there is no more questions, I would like to thank again to Ismael for his great presentation.